Now we have Bhavish Gopal, who will be talking about secure collaboration, graph processing made scalable. So welcome, Bhavish.
Hello everyone, I am Bhavish Gopal, and I'm here to present our work titled Collaborative Graph Processing Made Scalable. So this is a joint work with Siddharth Kapoor from University of Utah, Nishat Koti from Aztec Labs, Varsha Bhatt Kukla from IIT Tirupati, and my supervisor from Indian Institute of Science. So there are various real-world applications where the data is modeled in the form of a graph, and given their popularity, there are also various algorithms that are designed to derive information from this graph data. But in most of these cases, these graph algorithms are designed to work on a clear text, entire global graph. But in real world applications, these graphs could be distributed across different data owners. And moreover, they can also contain sensitive information which prevents these data owners from sharing this graph with others. And in such cases, analyzing this global graph becomes more challenging. For example, you can take a transaction network where vertices are bank accounts and edges are transactions. This transaction network itself would be distributed across different banks, where each bank would only see the accounts registered with them and the transactions pertaining to those accounts. Right? But these banks would like to collaboratively analyze this global transaction network for applications like fraud detection, anti-money laundering, etc. So, yeah, in this case, the network is containing sensitive information, so the banks would be unwilling to share this with others. Right? But this can be modeled as a problem of MPC, where these banks would act as parties in the computation, and their private data would be their partial view of this global transaction network. And whatever function that they would like to compute would depend on the underlying graph analysis that they want to do. So in this regard, in this talk, I'll be talking about our framework GRASP, which is a generic framework for securely realizing a large class of graph algorithms and exactly cater to the situation that I was talking about. The key contribution of our work is that we design a efficient and scalable framework compared to the prior works. And the key contribution is that in the prior works, the round complexity of the solution scaled linearly with the number of parties. And also, the solution had a very expensive initialization phase, which we eliminate. Right? And at the center of our work is this DCC paradigm, which is a new paradigm that was designed to for this vertex-centric graph computations. And it was designed to leverage these some local information that each of these data owners would have about their partial graph. And this allows us to achieve an improvement of up to 80 times in comparison to the prior works. So just to give a comparison about various works in the literature and where we stand. So a naive approach to realize some of the graph algorithms would be to represent the graph itself in the form of an adjacency matrix. And then you perform computations on this secret shared adjacency matrix or encrypted adjacency matrix. Right? But in MPC, this can be done in a constant number of rounds, like independent of the number of parties. But it would incur a communication complexity that is of the size of this adjacency matrix, which is V square. And most of the real world graphs are known to be very sparse, and this blow up in communication makes these solutions not very practical. Then there was this work called Graffiti, which improved over some of the prior works. And Graffiti, following along some of the prior works, worked on the list-based representation and achieved a round complexity, a communication complexity that is like logarithmic, log linear in the size of the graph, right? This is the end-to-end communication complexity. But you can see that it has high round complexity. Specifically, there is an expensive one-time initialization in Graffiti, which incurs a round complexity logarithmic in the number of vertices. And also it has round complex that is dependent on the number of parties. And following this, there was other work called Ring SG, which actually improved the round complexity, made the round complexity independent of the number of parties, as well as the graph size, and also incurred a communication complexity, you can see, which is independent of the number of parties. But this comes at a cost of poor privacy guarantees. Specifically, they had a corruption threshold of 1, which means that any two data owners collude together, they can learn some information. But in comparison, our framework GRASP achieves a round complexity that is independent of the number of parties as well as the graph size. And it also has a communication complexity that is linear in the graph size. Okay. And also it has the best, it can have the best corruption threshold where it can tolerate up to a collision of up to n minus 1 data owners. So next I'll give a bit of an overview about how Graffiti works, because our solution also builds on top of Graffiti, followed by explaining how we improve Graffiti. So Graffiti, following along some of the prior works, like GraphSC, it also operates on a list-based representation of the graph, known as data-augmented graph list. Over here, the graph itself is represented in the form of a list, which has an entry for every vertex and edge in the graph. And the vertex itself, and every entry is represented using a tuple, which consists of the source information, destination information, is the vertex, whether the entry is a vertex or not, and all the data associated with the vertex. Right? So a vertex itself will be represented like this, and an edge would be represented in this way. So given this, Graffiti facilitates secure computation of what is known as message passing algorithms. So these are algorithms that operate in multiple iteration, where in every iteration, a vertex is going to send its current state through its outgoing edges, and every vertex is also going to receive and aggregate messages through their incoming edges, and use this aggregated information to update their state. Right? And a lot of popular algorithms can be represented in the form of message passing computation. Just to give an example, let us say you want to identify all vertices reachable within a k-hop distance from a particular target vertex. What you could do is you could set the state of the target vertex to be 1 and state of all the other vertices to be 0. And you do one iteration of message passing where the state is propagated through the outgoing edges and aggregated through the incoming edges. You would identify all vertices reachable within 1 hop distance. And if you repeat this for k many iterations, you could identify all vertices reachable within k hop distance. Right. Okay. So now the question boils down to, given the list-based representation, how would you efficiently realize these primitive operations of scatter, gather, and apply, right, where you update? So for this, Graffiti relies on reordering this list-based representation on different ordering. Specifically, they have 3 different ordering. One is the vertex ordering, where all the vertices occur first together, followed by all the edges. And then they also use source ordering, where every vertex is immediately followed by their outgoing edges. And then you also have destination order, where every vertex is immediately preceded by their incoming edges. So they reorder this graph list into these different orderings to achieve this scatter, gather, and apply. And I'll just explain how that works. So on a high level for scatter, right, I'm also call it propagate, but yeah, it's scatter. What you need to do is the Graffiti requires you to reorder the list representation in the vertex order, where some linear operations are performed, followed by reordering the list to a source order where some linear operations are performed. And similarly for gather, the list is reordered in the destination order, followed by reorder where some linear operations are performed, followed by reordering it to the vertex order where again some linear operations are performed. Okay, so I'll just give a brief overview of how this scatter, gather, and apply works. So consider that you have the following graph, which is, and this is the underlying list representation of the graph in source order. And this is the vertex data component which you want to propagate to the outgoing edges, right? So if let us assume that there is the source ordering of the vertex, you can just perform a linear scan and then compute the data that is there in this edge as the prefix sum of all the data present in the previous entries, right? If you do this, what you would get is, for some of the, especially for the edges of the first vertex, you would aggregate the correct data, but for the edges of the other vertices, you would aggregate the correct data plus some error term. And the idea Graffiti had was that you first use the vertex order to correct for this error, so that when you compute this prefix sum, it captures the correct propagated value. And if you look, and the intuition behind that is that if you look at this particular edge, the error propagated or error in this particular edge is exactly the data propagated in the previous edges, right? So the idea is that you first sort the list in the vertex order, where you compute the difference between every consecutive vertices, and you propagate, basically you propagate this data in the next step, right? So once you've computed this difference, you reorder the graph in the source order, and then now when you do a prefix sum, it captures the correct propagate. And if you look over here, all the steps involved during this linear scan are just additions or subtractions, which is non-interactive in MPC. So the only cost that would be incurred is for this transition. And similarly, the idea for gather is also similar. Let us say you have the destination order where there is already these values that have been scattered or propagated to the edges, and you want to aggregate them towards the vertices. For simplicity, let's consider the aggregation operation to be addition, but Graffiti can support any linear aggregation operation. Yeah, so let us say you have the destination order where every vertex is preceded by their incoming edges. You can do a linear scan and compute the data aggregated at vertex to be the sum of all the data in the previous entries. If you do it this way, again, all the vertex are going to aggregate the correct data plus some error which is accumulated. Again, the idea is that the error over, for example, in vertex 2 is exactly the value aggregated in vertex 1. So you can use the vertex order to correct for this error. So gather this way involves performing prefix sum in the destination order, followed by a transition to vertex order where you correct for the aggregated data. Right. Okay. Finally, apply involves updating the state of the vertex based on the aggregated information. Unlike scatter or gather, this does not require any linear scan or any specific ordering, because this is local to every entry in the graph, in the list. Okay, so just to summarize, one iteration of this message passing, where you're doing scatter, gather, and apply, involves many reordering of this graph list. Specifically, you start with the vertex order, which is reordered to source order, and this collectively realizes scatter. And then you have transition from source order to destination order so that you can start performing gather. And gather involves transition from destination order back to vertex order. So this is how one iteration of message passing looks like in Graffiti. Now, if you look at how these transitions can be realized, a straightforward approach is to sort this list into the required ordering, right? But secure sort is known to be expensive in MPC. And it would require like order of log v many rounds if you want to do it in a naive way. But the work of Araki et al. Observed that the ordering, the transitions involved in this computation, they remain same across multiple iterations of message passing, right? Specifically, every iteration you want to go from vertex order to source order to destination, and back to vertex order. So they observe that you can do the sorting. You don't have to do the sorting again and again. You can do it once, and then you can use this information. You can generate a secret sharing of the mapping that realizes this reordering. And then you can, from the next iteration, for the subsequent iteration, you can just apply this mapping efficiently using this primitive of secure shuffle, which has like round complexity. Oh, sorry, it's not order of one. It will be dependent on the number of parties. So this is how it's going to work. So let's say you have vertex ordering, and you want to go to source order. First, what you could do is you could apply a random permutation on this list and reorder this list with in some random order, and then you can sort this list back to source order. However, observe now that this particular mapping from this random order to source order can be made public because this is anyway a randomly ordered list, so it doesn't leak any information about the relation between vertex order and source order. Right? So this is how it would work. Like in the first initialization, they would shuffle, apply a random permutation followed by a secure sort. But for the subsequent iteration, this mapping can be made public, and you only have to apply a random permutation followed by a public mapping. Right? And applying the shuffle would require order of n rounds, where n is the number of parties. Okay. So now if you look at what are the overheads in graffiti, first thing is the expensive one-time initialization phase, which requires expensive sorting operation, and also it has like both rounds dependent on the number of parties as well as the graph size, right? Although it is claimed to be a one-time thing, in practice, like in several applications, it can take up to like 70% of the total runtime, right? Which is a major bottleneck. And second is also that the message passing, it requires applying the shuffle protocol, which has round complexity dependent on the number of parties. So if you have large number of data owners, which could be the case in several applications, this message passing also becomes a bottleneck. So in contrast, graphs, our framework actually eliminates this need for expensive sorting in the initialization phase, and it also makes the round complexity of message passing independent of the number of parties. And I'll just give an overview of how that works. So we first propose a new approach for realizing message passing on graphs, known as DCC paradigm, which is decompose, compute, and combine. So let us assume that you have a graph like this, which is distributed across three parties, P1, P2, and P3. And let us say you want to perform message passing on this graph, and these are the current states, right? So you can observe that for the next state of, say, particular vertex V6, it would depend only on its immediate neighbors V2 and V4 over here, right? So to compute the next state after message passing for all the vertices belonging to party 3, what you could do is you could consider only a subgraph that has all the vertices belonging to P3 and their immediate neighbors, right? And the advantage of doing this is that the topology of this particular graph is already known to party 3, who is participating in the protocol. So this is the high-level idea. So our idea for message passing has 3 steps. First, we decompose the graph itself into different subgraphs, each known to at least one of the participating data owner. And then we perform message passing computations on each of these subgraphs, and we optimize the message passing computation on each of these subgraphs using by leveraging the knowledge that each of this at least one data owner knows the topology of each of this subgraph, and we leverage that to optimize the message passing. And finally, after performing this message passing, we combine the information of all the subgraphs together to realize one iteration of message passing. And then this will be repeated across multiple iterations. Okay. So I'll just give an overview of how that exactly works and where our improvements come in. So in our framework, the graph itself is represented instead of a single list, it's represented using multiple lists. So we have a vertex list that would be secret shared among all, and then there are different edge lists, and these are specifically containing like E1 would contain edges that terminate in vertices belonging to party P1, right? And similarly E2 and E3. So this is how the graph would be represented. And decompose phase involves generating the list representation of all the subgraphs, like similar to what graffiti uses. So that would just be collecting, you already have the vertex list, you just concatenate it with the required edge list, and that would form the required list representation of all the subgraphs. And then you would perform computation on this, which is again similar to what graffiti does, where you will do transition from vertex order to source order on these subgraph lists, and source order to destination order, and destination order back to vertex order. And like if you want to do it in a straightforward manner, you can do what graffiti did. All the parties could apply a random permutation followed by a public mapping that was generated using a secure sort. But the observation here is that this subgraph, the topology of the subgraph is already known to party 1. Let's say if you're considering subgraph 1, it would be known to party P1. And in this way, instead of using a random shuffle, you can apply actually a random permutation that is known to one of the parties. And then followed by, instead of sorting, this public mapping can be computed locally by this party who knows the topology and can be sent to every other party. Right? So in this way, we are using a weaker primitive instead of shuffle, which is known as permute plus share, which allows parties to apply a random permutation known to one party. Right? And again, this public mapping, you don't have to sort to compute it. You can just compute it like party P1 can compute and send it to all. So in this way, the round complexity for message passing is reduced to made independent of the number of parties, and the initialization phase also does not require sorting anymore. Okay. And finally, to combine the information, you just have to take the respective vertices from that belongs to those party in those subgraph, and then you just have to collect the shares and then combine them. So this step will also be non-interactive. So just to summarize, decompose could be just non-interactive operations. Combine also has non-interactive operations. Compute has just invocations of permute plus share, which is round complexity independent of the number of parties. So yeah, I think I don't have much time, but we also implement and benchmark graffiti and compare it with our, compare our framework with graffiti for the application of page rank computation. So just comparing the improvements in the message passing computations without initialization, we have up to 14 times improvement in comparison to graffiti. And if you look at the end-to-end improvements, we have up to 78 times improvement in comparison to graffiti. And also, to perform 10 iterations of page rank computation among 25 data owners, it takes less than a minute to actually compute using our framework, which shows that it's highly scalable. So yeah, that concludes my presentation. I'm open for questions.
We have multiple minutes for questions.
So thanks very much for the presentation. I was wondering if your framework is restricted to linear apply functions, or can you also do something highly nonlinear, like computing minima for Dijkstra or usual graph algorithms, or is it just the three examples that we always had with cut score and truncated cut score, where the apply function is a linear thing?
Right. I think the round complexity and everything that I mentioned was with respect to linear functions. If you're using nonlinear functions, you'll have to fall back to what prior works does, and it would incur a logarithmic many rounds. And I think, but you can do it in linear communication still.
Okay, thanks.
Do we have more questions with Bhavish? Then yeah, thanks Bhavish for quite a practical talk.